So in this video we're going to have a wee look at the answers to the equilibrium questions that I sent you. Obviously if you're trying to be sneaky here and look for the answers where you've sent them, I can't stop you, that's up to you. But what I would say, you're going to get more out of this if you've had a go at these first, because some of these are quite tricky questions, so it's good practice if you have had a go at looking at them beforehand. First question is question 8, so it's a multiple choice question. There is quite a lot of working out to do with it. It's giving you an equilibrium between sulfur dioxide SO2 and sulfur trioxide by adding oxygen to it. Gives you the enthalpy change information for it as well. So it's got -192, therefore it must be exothermic. So you've got a few options here for changes. In option A, an increase in concentration of O2 will increase the equilibrium amount of SO2. So let's think about that. If we increase the amount of O2, according to Le Chatelier's principle, the system or the equilibrium will want to use it up in response to that, to oppose that change. That will cause the equilibrium to go to the right hand side to decrease the O2. If I decrease the O2 by going to the right hand side, I'm also going to decrease the amount of SO2 because it's also on this left hand side, so one of the reactants. So that can't be right. The SO2 will go down if I increase O2. B, a decrease in pressure will increase the equilibrium concentration of SO3. So talking about pressures with gas particles, we're always going to be counting molecules on each side. So on the left hand side we've got 2 SO2s and 1 O2. There's 3 on the left. On the right hand side you've got 2 SO3s. So decreasing the pressure, so according to Le Chatelier's principle, decreasing pressure, the system wants to increase the pressure. It can increase the pressure if it moves it back to the left hand side where there are more gas molecules. So moving the equilibrium to the left hand side will decrease SO3 because it's on the right, so that's actually wrong as well. C is the correct answer, we'll come back to it in a second. We'll talk about why D is wrong first. In D, removal of SO3 from the vessel will increase the concentration of SO2. That's another concentration one. So decreasing SO3, the system wants to make more SO3 in response to that. To make more SO3 we move to the right hand side, and that will actually use up your SO2, so that's not right as well. It'll decrease the concentration of SO2. So C is about temperature is the correct answer. Increasing temperature will increase the equilibrium concentration of SO2. So if I look at my delta H value here, it's a negative sign. We talk about the fact that means it's exothermic. It means it's exothermic in the forward direction though, so I always like to write on exo forward. That means reverse must be endo. If I increase temperature, the equilibrium will want to cool itself down again. It can cool itself down again if it favours the endothermic part of the reaction, the reverse reaction. If it favours the endothermic part of the reaction, going right to left, that will move the equilibrium to the left hand side. If we're looking at the effect mentioned in the option, we're saying that increased temperature will increase the concentration of SO2. That looks correct because if we favour the endothermic reaction to cool it down, moves the equilibrium to the left hand side, that's going to give you more SO2, which would increase its concentration. So C must be the correct answer. Next question, obviously a theory question. It gives you an equilibrium between carbon dioxide, hydrogen, methanol and water. They're all in the gas phase. Part A is a little kind of like definition question, which is just straight out of your notes. 2 marker, what do you understand by the term dynamic equilibrium? So there's always 2 parts to that. The first marker is always for the bit about the rates. So the rate of the forward reaction is the same as the rate of the reverse reaction. So it's tempting to leave it just like that, but that's only 1 mark. You have to talk about the implication of those rates being the same. If the rate's same forward and backwards, it means the concentrations are locked in and can't change. So how you write that is that the concentration of the reactants and products remains constant. So that's your second mark. Part 2. State and explain the effect of increasing the pressure on the position of the equilibrium if temperature remains constant. So obviously it's a pressure one. We'll just check it. Everything's a gas, that means it's fine to talk about number of gas molecules. We do a little bit of a count. 1 CO2, 3 hydrogens give you 4 on the left hand side, 1 methanol, 1 more gives you 2 on the right hand side. So let's think about the effect. We're increasing pressure, so thinking about our logic again. Le Chatelier's principle, if I increase the pressure, the system wants to decrease the pressure. It can decrease the pressure if it favours the right hand side, because there's only 2 on the right but there's 4 on the left, so that will allow the particles to spread out a wee bit more. 2 mark question. There's going to be 1 mark for state and 1 mark for explain. So first is a statement, which is simple enough. We just talked about the idea that the equilibrium moves to the right hand side. 1 mark for that. Second mark is just that logic we just used there, counting up your molecules and comparing them. So the way it's written in the mark scheme is this. This got you second mark. 4 moles of gas on left hand side in comparison to 2 moles of gas on the right hand side. Now that did actually get you the marks. If I was doing this in the exam, I probably add a wee bit more just to make it fully explained. What you mean by comparing 4 to 2 is that there's less molecules or fewer molecules of gas on the right hand side. So I would just add a wee bit the fact that we're favouring the side with fewer gas molecules with an increase in pressure. But strictly speaking, that wasn't really needed, but I would add it in anyway. Part 3. If the temperature increases, the equilibrium yield of methanol decreases. Deduce the sign of the enthalpy change. We're going backwards here. It's telling you about an effect of changing temperature. You have to work back to work out what that means for your delta H value. So let's think about this. Temperature is increasing and the yield is decreasing. By yield of methanol, we're talking about the amount of this particular product. So if the yield has decreased, the equilibrium must have moved to the left hand side because we're moving away from the product. Okay, let's again think about the idea that the temperature is increasing. If you increase the temperature of an equilibrium, the equilibrium wants to decrease the pressure in response to that. To decrease the pressure, you're always going to favour the endothermic part of the reaction. So in this case, if we're moving to the left, the backwards reaction must be endothermic. So this backwards part of it. The forward reaction must be exothermic. And again, we're saying that because the increase in the temperature moved it to the left. We must be favouring the endothermic reverse reaction. So now it's tempting to just write down, it's an exothermic reaction in the forward direction. It's not actually what the question is saying. No, it says deduce the sign of the enthalpy change for the forward reaction. So I have to use a wee bit of theory as well. I've worked out that the forward reaction must be exothermic. We need to know that exothermic forward reaction is always given a negative sign. So my first mark is just the idea that it's a negative sign for the enthalpy change in the forward direction. Do you have to explain it though? Explain your reasoning as a second mark. Again, it's quite open-ended, but I would just go along the lines I just explained there. Increasing pressure, increasing temperature favours the endothermic reverse reaction, which I think makes sense in terms of what you have to go through to get that. That's pretty much what the mark scheme as well. They said when temperature increases, you shift in the endothermic direction, or you could just say the reverse reaction is endothermic. So it's quite open-ended. Anything along those lines gets you the mark there. Part B, 1 marker. Why would the equilibrium position remain unchanged if a catalyst was added? Again, we've touched on that before in the notes. Catalysts don't do anything to equilibrium, they only increase your rate, and they increase the rate of the forward and reverse reactions equally, so the position of your equilibrium doesn't actually change. So how you write that, the explanation would be, so you're increasing the rate of forward and reverse reactions by the same amount. Okay, on to the right hand side then. Slightly shorter question. You've got nitrogen 2 oxide reacting with oxygen at full equilibrium. Similar kind of setup to before. It's a bit more by the book, this one. It's just asking you to describe and explain the effect of these following changes. So first one's temperature. We're increasing the temperature of this equilibrium. Looking at the delta H value, it's a negative sign. That therefore must mean the forward reaction is exothermic because it gives out heat. Reverse reaction must be endothermic. If I increase the temperature, the equilibrium wants to cool itself down. It's going to cool itself down by favouring the endothermic reaction, which goes backwards. That means the equilibrium position must move to the left. So first mark is equilibrium moves to the left. Again, it's quite open-ended with the second one for the explanation. Probably it'd be fine just to say favours the endothermic reaction. If I want to be super careful, I probably would say the endothermic reverse reaction. In this particular mark scheme, it's quite open-ended. It just says for that second mark, to absorb heat or to favour the endothermic process. So we've covered it there. Increasing pressure, so hopefully you know by now, if it's talking about pressure changes, you're going to be counting gas molecules. Let's look on the left hand side, 2 NOs and an NO2 makes 3. On the right hand side, there's 2 NO2s, so we've got 3 versus 2. Increasing the pressure, the system wants to decrease the pressure in response to it. It's going to favour the side with fewer gas molecules, which is the right hand side. So we're going to move the equilibrium to the right. And again, I always think it's good practice to actually explain what your numbers are for left and right hand side. So 3 gas molecules on the left. And there's only 2 on the right. And therefore you're favouring the side with fewer molecules. Final one we've seen before, adding a catalyst does have an effect. I'll give you 2 marks in this case because it's not telling you that it doesn't have an effect. You have to explain that first. So first mark is no effect on equilibrium. Your explanation is the same again, so it speeds up forward and reverse reactions. Equally. So on to the next page, this question 13. So obviously the end of equilibrium intersection on some industrial processes, you have to know some specific facts about them. So first one is about the Haber process. Starts with you just knowing what the equation for that is. It gives you a hint though, write the equation for the equilibrium reaction. That gives the implication you can't just write the reaction in the forward direction, you need those equilibrium arrows in there because it's telling you it's equilibrium. So nitrogen reacts with 3 hydrogens, reversible arrows to make 2 ammonia molecules. Name the catalyst using the Haber process. That's just simple recall. It's an iron catalyst. And then part C, explain why the combination of a high pressure and low temperature would would increase your yield of ammonia. So our justification for this is, with a high pressure, you're looking at the number of gas molecules. On the left hand side, we've got 4. A nitrogen, 3 hydrogens. On the right hand side you got 2. So therefore increasing the pressure pushes your equilibrium to the right hand side to use up your gas molecules. So explaining that for 2 marks, you're talking about your difference in molecules. So again, number them and name them. So we got 4 gas molecules on the left hand side. Versus 2 on the right hand side. Therefore, equilibrium moves to the right hand side. And again, that should be enough for 2 marks, but just to make sure, and maybe just explain it fully, you've compared the gas molecules there. It's the idea that there's fewer on the right hand side pushes it to that side. So fewer molecules on the right hand side, that's why it's favouring it with high pressure. With low temperature, again you're talking about the enthalpy change for the reaction. Now this one's a wee bit tricky in that you have to actually remember whether it's exothermic or endothermic. It's not giving it to you in any part of the question. So the idea that we use a low temperature comes from the fact that the reaction is exothermic. So that's 1 mark for this. The reaction is exothermic. The justification for why you therefore use a low temperature is a low temperature favours the endothermic forward reaction. So if you think about that fully, so if we want to move the equilibrium to the right hand side, the forward reaction is exothermic, therefore a low temperature, which cools the reaction down. The reaction wants to heat itself back up again. It can heat itself back up again if it favours the exothermic forward reaction. That moves it to the right hand side. Question 6, multiple choice question. I actually think this is a very tricky question. It's quite kind of beyond the spec almost. It's giving you an equilibrium kind of reaction between bromine, water, the bromide ion, the bromine ion, and some hydrogen ions. Which one of the following reagents would move the equilibrium position to the right? What's tricky about this question is that some of these reagents don't appear to be any part of the equilibrium itself, which seems a wee bit hard to understand. A and D you probably put in the same bracket. Nitric acid and sulfuric acid are not found in this equation, but a certain part of the acid is. What you hopefully remember from before is that acids always produce hydrogen ions, which are in the equation. So nitric acid makes H+, sulfuric acid makes H+. So if I add either nitric acid or sulfuric acid, I'm increasing the amount of acid I've got, increasing the amount of H+ I've got. If that increases, the equilibrium wants to use it up. To use that up, it's going to move to the left-hand side. So that rules them both out because the question is asking about moving to the right-hand side. So increasing H+ is not going to do that. A and D are both out. Next one we'll look at is sodium bromide, option C. That's a little bit more by the book. We do see the bromide ion there. So if I increase the bromide ion, that's going to again move the equilibrium to the left-hand side, which is not what the question is asking for. It wants to move to the right. So that's going to rule that out again. So by elimination, we probably could work out it's B, but we want to justify why it is B. Sodium carbonate is not in this equation. There's no sodium ions, there's no carbonate ions. What you have to think about is what sodium carbonate might do with the things in the equation. You might remember, or you should remember, sodium carbonate reacts with acids. It's like a form of a neutralization reaction. Acid plus carbonate goes with salt plus carbon dioxide plus water. So if I add sodium carbonate to this equation, it's actually going to use up the H+, because it neutralizes it. That will decrease the concentration of the H+. If I've decreased the H+, the system wants to make more H+, by moving the equilibrium to the right-hand side. So that is the actual answer there. It's because your sodium carbonate uses up H+ by neutralization that the equilibrium moves to the right-hand side to replenish that H+. Final side, got a question on polytetrafluoroethane and the process for it. Part 1, explain what's meant by the term thermal cracking. Obviously that's nothing to do with equilibrium, it's like an organic chemistry question. Thermal cracking is when a molecule is broken down using heat. Because that explains both parts of it. Cracking means broken down, thermal cracking means you have to use heat to do it. Explain using delta H value whether the reaction is exothermic or endothermic. Maybe seems a little bit of a trick question. You just have to look for the number up here, and hopefully you're confident enough the fact that +128 would therefore be endothermic. That wouldn't actually get you the mark though, because it's asking you to explain it. You might think, well, what is there to explain? It's just a number. If you think about what you're actually doing in your head to work out that it's endothermic, you're focusing on the sign, and even if you're not thinking about it explicitly, you're doing the wee checklist in your head that a positive sign is always endothermic. So it just wants you to explain that. So it's endothermic as delta H is positive. And I think it's just looking for that in the question just so you can't guess 50-50. You actually have to justify it with the sign. It wants you to show that you know the sign controls whether it's exothermic or endothermic. Part 3 of this I'm not actually the biggest fan of as a question. I think it's a bit vaguely worded. Explain in terms of reaction rate and equilibrium whether a high or low pressure should be used. It's bringing in two things here, rate from the topic kinetics and equilibrium from the equilibrium topic. And that is asking you which one would you pick if you could pick a high or a low pressure. If we think about equilibrium first, because that's what we're on, we want to make lots of the right hand side because it's the process to make this product here. To favour the right hand side in terms of pressure, I want to count the molecules again. So I've got 2 on the left hand side, I've got 1, 2, 3 on the right hand side. To favour the right hand side, I therefore would probably use a low pressure, because that would make the equilibrium move to the right to make more gas particles. However, if I've got a low pressure, that's going to slow the reaction down, make it like a slow reaction. It'll decrease the rate. So kind of got a bit of contrast there, and I have to justify which one I think is more important, which is why I think it's not a very good question, because it doesn't give you any indication about which will have a bigger effect. In a lot of cases, probably your rate won't be affected that much by pressure. Pressure can only go up and down by a certain amount in terms of what you can do in a factory. So it's actually probably the equilibrium yield you're going to be more interested in. But again, I don't think it's very fairly worded. But anyway, looking at the wording of the mark scheme, it's 1 mark for the idea that you'd probably want to use a low pressure. Your justification for that is whilst this will lower the rate because it's low pressure, there are more gas molecules on the right hand side, so yield will increase. So that's what they're looking for. Again, as I said, I don't think it's very fair. If you've got any big problem with that, direct them those problems to C and not to me. I didn't write the question, but that's what they're looking for in the mark scheme. Part 4 I think is a little bit more fair because it does actually make sense. Explain in terms of reaction rate and equilibrium whether high or low temperature should be used. Again, same kind of question, talking about rate and equilibrium, but luckily they do match up in this case. So we look at equilibrium first, because that's the topic we're on. It's got a positive sign, therefore the forward reaction must be endothermic. And hopefully we're happy by now. If the forward reaction is endothermic, I'm going to favour the forward reaction with a high temperature. So that's good for us. High temperature would make a large yield, favouring the endothermic reaction. Luckily, a high temperature will also increase the rate, because we know from kinetics, if you increase the temperature, you're going to have more particles above the activation energy, gives you an increased rate of reaction. So what the mark scheme look for here is straightforward enough. You would want a high temperature. Then 2 marks for just explaining that. You talk about the reaction, we talk about forward reaction is endothermic. So moves the equilibrium to the right hand side. And then regarding the rate, it's not actually looking for a really in-depth explanation, just the idea that high temperature increases the rate of reaction. Finally, a little bit of a theory question to finish it off. Hydrogen chloride is a product of the reaction. Describe a chemical test for hydrogen chloride gas. That's going back to Module 1. So remember, they can bring in Module 1 questions in Module 2. Hopefully you remember it's a rod dipped in concentrated ammonia. It should say ammonia solution, because it's the liquid form of it dissolved in water. Remember, ammonia itself is just a gas. 1 mark for rod dipped in concentrated ammonia solution. If you bring that towards hydrogen chloride gas, you should see those distinctive white fumes or white smoke. So that gets you the 2nd mark.